Hello again, students. We're continuing our study of simple harmonic motion. So last time we were talking about functions that describe the simple harmonic motion, and we could use the sine function or we could use the cosine function, and our book makes the decision we're going to use cosine. So something that's moving sinusoidally is described by the cosine of the time times the angular frequency omega. So here's time, here's our angular frequency. And then just in case maybe we need to shift the sine wave or cosine wave to the right or to the left, so that's what this phase shift is for. Usually we leave it 0. And then we can have big oscillations or smaller oscillations, and so that's what the A is for. And that's the amplitude of the oscillations. And I've graphed here the position as a function of time for delta equals 0 of an oscillator. Now what we want is to find the velocity function and the acceleration function for our simple harmonic oscillator. And we know that the slope of a position graph gives us the velocity. So thinking that way, well, the slope here is 0. And the slope here is negative. And the slope here is 0. So what's 0 at time 0? Well, the sine function does that. Now the sine function, it becomes positive maximum at pi over 2, but this function here is going negative. All right, it's sloping downward. Okay, so we're going to add a negative sign. And then, when you have a bigger amplitude to your oscillations, your velocities are going to be bigger too. So that means we need the A. And when you vibrate faster, you're going to have bigger velocities. Yeah, okay, so we need the omega. And then the rest is the same as before. So that gives us the velocity as a function of time. And just in case I didn't say it before, when you see dx dt, that's the calculus way of saying slope. Right? So, all right. Now, moving on, what about acceleration? Well, you go through a similar process, and with the slopes and all of that, and you get that the acceleration is, once again, it depends on the amplitude. It turns out that it's going to depend on the angular frequency squared, and it's going to come back to the cosine here. So you have cosine when we're talking about position, we have sine when we're talking about velocity, and we have cosine again when we're talking about the acceleration. Now that sets up something kind of interesting. Let's scroll down a bit here. You see, when you compare let's see. Right? So we have almost the same thing here. We've got cosine omega t plus delta. Here we have cosine omega t plus delta. We have acceleration. We have acceleration. The only difference is that there's a minus sign here and an omega squared. So we can do something very interesting. You see, the acceleration is minus omega squared times the position. And so now we're going to go off into calculus land here. This means that the second derivative of the position is equal to minus omega squared times the original function. And so you see, so there's a really special calculus thing. This is like for third year calculus. You have the derivative of a function equal to itself times a constant. That kind of thing is called a differential equation. And differential equations are very important to engineering and also to biology. For example, the coronavirus, the spread of the coronavirus could be described by a differential equation, just like this. One of the important differences, though, is in biology, this would be a plus sign, not a negative sign. So a positive sign means exponential growth, and a negative sign here causes oscillatory motion. But anyway, I'm getting off on a tangent here. Just suffice it to say that the math gets very interesting. Some people like that kind of stuff. All right, so now let's talk about energy in oscillations. So we're going to start with a mass that's on a spring. So yeah, it's all set up to do oscillatory motion. And we're going to have it sitting there at x equals 0, and it's not moving. So we have the potential energy, which is 1/2 kx squared, right? That's the potential energy of a spring, is going to be 0 joules. Now, we push to get it to a location x, which will be A. A obviously is going to become the amplitude. At this time, the potential energy is 1/2 kA squared. Now, we let it go, and the spring is pushing it to the left. So the spring pushes it to the left. It's accelerating to the left. As the spring pushes, it's losing its energy. The spring's energy is going into the mass, increasing the mass's kinetic energy. So now it's got velocity at this place. Now we're looking at it now that it's back to its starting place where the spring is relaxed. At this point, the spring isn't pushing or pulling on it, and all of the energy is come out of the spring, and it's all been transferred into kinetic energy. And so the mass is going with this kinetic energy 1/2 mv squared. So as all of this is happening, right, well, from the moment that we let go, this system conserves energy. So the kinetic energy plus the potential energy, which is in the spring, added up, that's the total energy, it stays constant. And as the mass bounces back and forth, boing, 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 the total energy stays the same, but the kinetic energy goes up and down, and the potential energy goes up and down as well. And they go up and down in opposite times, right? So when the kinetic energy is going down, let's say, then the potential energy is going up. And that is what you see in this graph. So the blue here is the potential energy. And we started the mass to the right, and the potential energy was 1/2 kA squared. Then we let it go, and it starts moving fast, and the kinetic energy is increasing. This is the kinetic energy. And the kinetic energy becomes a maximum when? When does it become a maximum? Well, you see, it became a maximum when the mass passed by the relaxed place of the spring, right? Here's where the spring is relaxed. It's neither pushing nor pulling, and so there's no energy in the spring at this place, and it's all kinetic energy. So that happens here. This 0 line, that's where we started. That's the relaxed place for the spring, and so this right here matches up with this maximum kinetic energy and 0 potential energy. Now the spring starts. So that we keep going. Now, when we get over to here, the spring has been stretched, right? It's gone out in the opposite direction. So now we've got lots of energy, all of the energy is back in the spring. The slope here is 0, so we know that the mass has stopped, so we have 0 kinetic energy. Now the spring is pulling back on it, and at this place, the mass has now moving to the back to the right, and we have maximum kinetic energy again, and the process starts all over again. Okay, so I have here one of the PhET simulations to illustrate what I'm talking about. When I started up the simulation, the spring was relaxed and it was here. And then I pushed the spring up to here, and now the 100-gram mass is being held by this compressed spring. And let's take a look at the energy graph over here. So over here it says E total. That's going to be the sum of the potential and kinetic energies. Right here, this is the potential energy of the spring, and then over here you've got the kinetic energy, which is currently 0 because nothing is moving. Let's see what happens when we make things start to go. So look at what's going on here. When you get to the middle, let's see if we can stop it when it gets at the middle. There, I stopped it at the middle. So now all of the energy is kinetic energy. The total energy never changes, but all of the energy is now kinetic energy, and the potential energy is 0. Also, just notice the frequencies here. So right now it looks like it's about 5 or 6 seconds per oscillation, right? Boing. And then I have to wait. And boing. So just going with the boings, right? Boing. But now look at what the potential energy is doing, for example. So boing, boing, boing. So the potential energy goes up and down at twice the frequency as the oscillator itself. And the kinetic energy also goes up and down at twice the frequency of the oscillator. Yeah, so the effect that we saw in the simulation, where the energy is bouncing up and down at twice the frequency as the oscillator itself, you can see that in these graphs. Here, you've got the oscillator at its starting point, and then it goes to its left extreme, and then it goes back to its starting point. In that period of time, the potential energy has gone from a maximum to a minimum, back to a maximum to a minimum, back to maximum. So it's gone up and down twice. And the kinetic energy has also twice the frequency. Now, what about the fact that the total energy here stays constant? Well, here we can prove that that actually happens. So let's write the potential energy. Right? The potential energy is 1/2 kx squared, but x is a cosine omega t, so you square that. And so you get that the potential energy is 1/2 Ka squared times the cosine squared of omega t. By the way, we're leaving out the phase shift, right, for simplicity. Now, how about the velocity and the kinetic energy? So kinetic energy is 1/2 mv squared, but the velocity, if you go back, is minus a omega sine of omega t. Now you're going to square that, right? It's 1/2 mv squared. And so you find that the kinetic energy is 1/2 do some algebra here. Now the thing here, we have omega squared, right? We want to get rid of that, but we can do that because we know that omega is the square root of k over m, right? That's something from before, the previous video. And so once we've got that, then the masses go away, and we have that the kinetic energy is 1/2 Ka squared sine squared omega t. Now, the total energy is the potential energy plus the kinetic energy. So we're going to add this thing and this thing. So here we are adding them up, and we get that the total energy of the system is 1/2 Ka squared. Now, I went through all of this pretty quick, and you kind of need to go back to the book to study this, because the homework problems, they start out easy, right? They're just like, oh, okay, what does the oscillator do? It's bouncing left and right, and just figure out its motion. But then things get ugly, because we start talking about the energy. The homework problems start talking about the potential energy, the kinetic energy. And to work through these problems, you need to have these relations handy, because they're going to get used. Okay, now the book talks about the difference between oscillators, where you have the spring and mass moving horizontally, and the spring and mass moving up and down. And actually, there's very little difference in the way they operate. And as I've been explaining stuff, I really haven't made any distinction between the two. But there is a small difference. I mean, when you're talking up and down, we have both the potential energy of the spring and the potential energy of gravity, right? So when you're up high, some of the potential energy is in gravitational potential energy. However, it makes no substantive difference in the way the spring oscillator behaves. The only difference really is where you're at when the oscillator is just not moving. If you have a mass that's just hanging from a spring and it's not bouncing up and down, gravity is going to cause the mass to pull on the spring and stretch it somewhat. And when you decide to, okay, let's make it bounce, so you can either pull it down or push it up. Let's say you push it up to here, and so this displacement here will determine the amplitude of the oscillations. When you let it go, it's going to bounce up and down, up and down. If you had the same setup, but let's say out in space, and this was like some heavy object, let's say the International Space Station, and a spring and a mass, the same spring would not be stretched at the beginning, right? Let's say you're just setting things up. The mass is now not moving, and so the spring has no energy in it. Now you decide, okay, let's make the spring oscillate, the mass oscillate. So you started off by pushing it up, compressing the spring somewhat, and let it go. And so the amount that you move to the mass, that determines the amplitude, and it's going to be bouncing back and forth between these two limits. Now, the book carefully explains this and proves that the motion won't be different. It'll be the same motion. And so I'm not going to go through all of that, but maybe it's worth taking a look at it. And we have an example here in the book that goes through this process. So that's it for the energy of oscillations. I really have only scratched the surface, and it's going to be up to you to read the book pretty carefully and to work those homework problems. So yeah, work hard. And we're almost there. This is almost the end of the semester. You're doing great. So hang in there. Bye bye.